Okay, so this is the implementation session for the what for this week. Okay, and so discrete filter design. Okay, clear all, close all, and CLC. Okay, so the week 9 M script X, it's given in here. Okay, and so the X1 is related to body plot creation. Okay, so first of all we need to define the F, the frequency spectrum in here, just like this one, the log space -1, 10 over -1, 10 over 1, and 500 points can be created in here, just like this one. Okay, 0.1 to 10 Hertz for 500 points. Okay, and so the omega should be calculated in here, 2.pi.f. Okay, and so S must be equalized with what, the 1i times omega. Okay, these are transformation for the what, for JW, and H can be built with what, the 1 dot divided by S plus 1. Okay, so after that we need to calculate the magnitude and the phase. Okay, the magnitude is equals to 20 times log 10 abstract h. Okay, and phase must be calculated with what, the angle h times 180 divided by pi. Okay, so for the plot the magnitude of these terms, we can write that the subplot, which is in here, 2, 1, 1, the first one is the magnitude, the second one the phase. Okay, the semilog x can be built with the f and the magnitude. Okay, and the grid on must be given here, the title body plot of HS is equal to 1 S plus 1. Okay, so the Y label is equals to what, the magnitude decibel, and the X label is the frequency values. Okay, Hertz. And after that we need to give the what, another form, which is the second, and the phase must be given in here, grid on and the frequencies and the phase. Okay, phase, which is given in the degrees and the frequency X label. Okay, we don't need to any title in here, and so if I run this code, and then we will have the what, the R body magnitude plot. Okay, and so at the 1 Hertz we have the 15 points in here, just like this one. This is the what, this is the R minus 15 point in here. But just see that if you push the any points in here, and so the Y must be equals to what, the at the 1 minus 3. Okay, and so we have the 0.16, which is the R cutoff frequency. Okay, this is the R cutoff frequency, and at the cutoff frequency we have the what, these points in here, x16, we have the minus 41 degrees phase relation, or the shifting in here. Okay, these are the body plot, and so we can analyze the R system based on these informations. This is the first example for the what, for R cases. Okay, and so in the second place we need to design to what, to low pass filter in the continuous time domain. Okay, low pass filter design, FC, for example, 100 Hertz in here. This is an example values. And so, in order to do that, we need to give the what the f log space in here -1 to 3 to 500 points, which means that we have the 0.1 Hertz to 1000 Hertz range in here, and omega should be calculated with what the 2 times pi times f, and fc can be set with what 100 values, and after that the rc value can be calculated with what the 1 divided by 2 times pi times fc, right? This is the correct relation of the what the r times c must be equals to what the this one for this low pass filter, okay? And so if this is the case, s is equalized with the what 1i times omega value, okay? And so the h can be given with the what 1 dot divided by rc times s plus 1, okay? And so how can we calculate the whole the values in here? Just like this one, we can calculate the whole the parameters in here. We can copy off the whole of these things, and so log 10 h this one, this one, this one, okay? And so if I rerun this code, and then we will have a flat response just like the butterworth filters, okay? And so we need to look at to what at the x at the y in here -3, right? And this is the -3 points, and so just see that the y is the amplitude or the magnitude of the r power energy in the decibel form, and so this decibel form is which is in here is to what the -3, right? And so this is the r cutoff frequency, which is equals to what the 100 values. And so if this is the case, and then we have the -45 degrees in here in the fast shift, right? And so what's the meaning of this -45? Which means that if we add the 1 s roots, or if we have the 1 pole in here just like this one, and then we will create what the -45 degrees fast shifting in here. But see that after the frequency values of the 100, and so we don't have the any signal in here just like this one. These are the what the continuous time, continuous low pass filter design, okay, at the x2. So in the x3 we need to implement to the what the low pass filter, but in the second order system, right? First of all, the fc can be equalized with what the 1000th value, and the zeta may be chosen as the 0.7. We will look at or analyze the zeta selection in here, okay? And so the omega c values is assigned with what the 2 dot pi dot fc, right? And so as always we do, f can be log spaced in here 2 to 4 and 4000th value, which is given in the 100 to 10 kilohertz values, okay? And so the omega should be applied to 2 pi f, and so what's the values of the transfer function in here? H can be calculated with what the omega c over 2 dot divided, and so the omega c dot over 2, this dot over 2, this is matrix multiplications in here, and so 2 zeta times omega c times 1i times omega, right? These are the case in here, okay? This is the representation of the r terms, because we don't need to use the what the I notation in here, just like this one, okay? And so if this is the case, and then we can assign the omega c over 2 values in here, just like this one. And so the rest of them is always with the what, with the same this code, and then if we assign these terms in here just like this one, and so if I rerun this code, and then we will have to what, to these notations in here. See, -6, but the cutoff frequency is already affected at what, the 100 values. And so what is the our wrong values in here? I think this representation is wrong. Just see that in the second order systems we have this kind of representations in here, right? And so the S must be assigned in here, just like this one. This is the omega values, and so the S is equals to what, 1i times omega, right? And so this must be equals to the omega S square and omega c. S must be given in here, right? The zeta and the S square, right? And so omega c dot over 2, and this one can be given in here. This is the exact representation of the R formulations. And so after that, if we rerun this code, and then we will have to what, to this kind of information here. Just see that this is the 10 over 3 or the 1000th value. And so if I choose the this seconds, and so this is equals to the what, -3 decibel in here, and so at the what, the 1000th value. And see that in this case we have the -9 phase degrees shifting in here, because we have the 2 poles in here at this phase. But if I choose the different frequency values in here, for example, we can easily set to what, the 500 values at the cutoff frequencies in here. See that this is the cutoff frequencies, right? And so this is the 1000th, but if this is the case, so -3, which is given here, just like this one, -2.79, okay? And so at the phase degrees we will have the what, -90 degrees. We have the 500 cutoff frequencies in here, okay? We can easily manipulate our algorithm based on these informations, okay? But how can we affect the 1000s, the zeta values? For example, if we have the zeta which is equals to 0.1, and so if I rerun this code, and then we will have the what y is equals to what, the dB is increased at these times. This is not useful for these algorithms, because if we have the cutoff frequencies in here, we don't need to what, this kind of peak, because at the cutoff frequency we need that our magnitude value must be equals to the what, -3 decibel, okay? And so how can we create this formation? If I choose the zeta 0.5, and so we may have the what, some increases in here. This is not useful right now. But if I choose the 0.9, and so we will have this kind of plots in here. See that? But at this domain, this y value -5.15 is equalized at the what, at this frequency, which means that our real case is set with the what, the -2.93, or the R cutoff frequency is shifting to what, the 736 value. And so the selection of the zeta is important parameters in here, just like this one, right? And so if we are using the what, the 0.7 in the zeta values, and so we can build our algorithm in the what, in the second order filtering systems, okay? The selection of zeta is important parameters in here, just like this one, okay? So this is the example 3, and also we need to return to the what, the example 4. And so in the example 4 we need to design the discrete low pass filter, okay? First of all, just remember that how we can do that. We can do these formulations using the bilinear transform with the what, with these formations, okay? And so we will implement this code on the what, on the Matlab implementations. And so First of all, the FC can be set with about 20 Hz desired cutoff. And so FS must be given in here 100 Hz. Okay, this is the sampling rate. These important parameters, guys. Frequencies. And the T must be equalized with what? The 1 divided by Fs. This is the sampling period in here. For the what? For the pre-warp, the cutoff frequency, we need to give the omega c values as with what? The 2 dot pi dot fc and also omega c prime values must be corrected with what? The 2 divided by t times tangential formation of the what? The omega c values times t divided by 2. Okay, this is the what? The pre-warped angular frequency. Okay, so beta 0 can be equalized with the what? With these formations, right? These are solution: beta 0, b0, b1 and a1, right? And so the b0 is assigned with what? The omega c prime divided by 2 divided by t plus omega c prime, right? These are formations. And so b1 is also equals to this one, right? Because the b1 is also equals to this one, but the a1 is different, right? A1 is equals to what? The minus divided by and divided by, there are two terms in here, 2 divided by t plus omega c prime, right? These are formations, but in the first place we need to give the what? 2 divided by t minus omega c prime. Okay, so this is the a1. And so how can we create the what? The test signal in here. First of all, the n can be equalized with the 100 values. Okay, this is the impulse response, just like this one. And so the x is equals to what? The 1 and zeros, n minus 1 and 1. Okay, this is the impulse input, right? For this case. And so y can be created for the pre-allocation form of these terms and 1, and so for n, which is equals to 2 to n, and yn can be equalized to the b0 times xn plus b1 x n minus 1, this is the index of these terms, the a1 times y n minus 1. Okay, and so the end should be given in here, just like this one. Okay, and so this is our results, or the filtered results of these terms. And so if we get the impulse response of these terms, and so we will get the what? The signal itself, or the filter itself. Just remember that. And so in order to do that, the h and f should be given in here with the values of the frec z and y and 1 and 1024, and fs values should be given in here, just like this one. Okay, and so how can we use this one? The figure, the plot, the f and the magnitudes of this signal, 20 log 10 in terms of the absolute values, the h can be given in here. Okay, and so this is the what? The title of the what? The frec to Mach responses of discrete filter design. Okay, that's the basic utilization of the what? These characteristics. Okay, and so we should give the what? The x label is equals to the what? The frequency value in the hertz, and y label, which is equals to the what? The magnitude values of the dB. Okay, okay, and so we need to give the grid on in here, and then we will run this code, and we will have to what? To this nomination system. -6 up to what? Up to 50 Hertz, because we have the sampling rate at the rate of the what? The FS 100. But if I choose the 1000s in here, and then we will have this kind of representations in here, just like this one. Okay, so where's coming from this -5 decibel formation? First of all, if we assign the omega c prime to what? To omega c, just like this one, and so if I rerun this code, and then we will have the same representations in here, see, but up to what? To 500 values of these cases. Okay, and so this is not important thing in here, but the frec function in here, frec s, and so the y and 1 and the number of evaluation points which is given in here, just like this one. And so if we have the default 500 1 2, but we can set these values in here, or we can set the what to 100 in here, and the fs can be given. Okay, and so if I rerun this code, and then we will have these formations. And so the frequency magnitude response of the R algorithm can be given in here, but with what? Fc is equals to what? 20 desired cutoff frequency in here. For example, if I choose the Fc as the 100, and so the R cutoff, which is given at what? At these nominations in here. See? Because if we have this information, and then we will relate to what the R nomination can be given or represented in this domain, just like this one. For example, if I set what? Z as equals to the what? To 1, and so each parameters cannot be defected by the other things in here, which means that in the what? In the frequency domain, we can have this kind of representation, not the 0 decibel one in here, but in this formation. And so how can I prove that? These nominations in here. First of all, we need to apply some frequencies in here, just like this one. For example, if I choose the X5, and so discrete low pass filter to apply the frequency characteristics in here, and so the FC, for example, 50 value, FS 1000 value, F equals to the what? The F5. Okay, and so this is the frequency of applied sinusoidal signal. Okay, and so A is 1, phi is 0, T is equals to 1 divided by Fs, and N Fs times 1. Okay, this is the number of samples. So after that, we need to take these parameters in here, just like this one, and so we need to copy it, and comments can be given in here. After that, the input signal should be assigned as the what? The N 0, 1, and N minus 1. Okay, and so the X A times sinus 2 pi F N T plus 5. This is a discrete sinusoidal signal. Okay, and so Y can be built with what? The zeros and 1. Okay, and so just remember that in the first case we apply the impulse input to this system, which means that if we have this condition, and so the -6 decibel can be given at this case, because this is filter itself. Okay, but if we assign or apply this signal in here, just like this one, the Y can be generated with the what? Based on what? The X and Y. And so how can we compare our results based on these informations? The figure, the plot is the N times t, right? And x should be given in here. At each sampling period, we need to assign the new x values in here. And hold on and plot n times t y. And title should be given in the what? The low pass filter. Okay? But the digital filter. Okay? And x label is the seconds or the time, sec, and y label is the amplitude. Okay, and also we need to give the legend in here. First of all, this is the input signal. This is the filtered, right? And so also we need to give the grid on. And so if I run this code and then our sinus signal, I'm sorry, maybe some error was coming in here, okay, and 0 1 2 n fs 1000 x and y, which coming in here, but n, I'm sorry, this n is replaced with what? With the numerical index in here. See? And so this n should also be copied in here. And so see, we have the same magnitude values, but with what? Some phase difference in here. The filter not ideal, but we can collect the whole forms of the what? The sinus signal in here. Okay? And so our cutoff frequency is the 50, but if I choose the what, this f value to what? To, for example, 40, what's the results? And so if I rerun this code, and then the R filtered response is different from the each other, right? And so we give the what? The 1, but the R filtered response is coming from the what? The 0.7 in here. For the what? For the 40. But if I choose the cutoff frequency to the applied signal, and then if I rerun this code, and then we will have the what? This kind of representations. Okay? The R total energy is diminished with the what? At least to what? To half of them. It's closing to what? The 0.5 points in here, right? But if I choose the 150 values in here, and so the R signal is the what? Is closing to each point. Okay, fs may be increased in here just like this one. And so if I choose this one, and then the R algorithm is what? Is 0.3 at this scale. Okay, and also maybe we can choose the what? The 250 values in here just like this one, and then we will have the 0.2 up to what? Up to 1. Okay, and so this is how we can implement our filter based on these informations. But we have some differences in here just like this one. The omega c prime can also be assigned with what? Omega c in here. So we maybe consider that the omega c prime is not used in here, or the pre-warp cutoff frequency. What's the result of these signals? The result of these signals doesn't change anything in here, but in some cases we can give what? Some another parameters in here just like this one. See, the omega c the figure, the plot omega c, and hold on, the plot the omega c prime can also be run here. And so see that the omega c prime is given in here just like this one, but omega c prime fc and fc, this is equals to each other, right? This is important, and so there's no change in this signal representation for the what? For our results. But in some cases maybe you can choose the what? For example, of 100 and the fs and the cutoff frequency is the 25, for example. And so if I choose the what 5, and so if I rerun this code, and then we will change the omega c prime is equals to what 200, but the omega c is equals to 157. Okay, this is important right now because because we had changed in signal representations in here, right? And so also we need to give the what this frag characteristics in here, h and f, right? But if I choose right now the omega c prime, which equals to the what, the omega c, and so our results is changed, right? See that? We have diminished results in here, just like this one. Or if I choose the 25 in here, and then we will have the what, the cutoff frequencies is diminished in here. Or we apply the 40 values in here, and so the R signal is also diminished in here, just like this one. Okay, but our filtered response is also diminished in here. But if I choose the pre-warped signal in here, and so the R signals cannot be have the desired point in here. Okay, and so if I choose the what, the 1000th value in here, and so the R results is similar with each other. Okay, we can apply the sinus signal or the some filters to what, to build these characteristics in here. Okay. So for the different sinus inputs, how we can select these conditions in here? First of all, we need to give the what, or we need to copy of the whole of these things in here, just like this one. And so x6 applying different sinus signals in here. Okay, and so I can uncomment all of these things in here. Okay, and so this is the 50, the fs 1000s, but the frequencies can be assigned with the what, the 5, 50 and 100s. Okay, a is equals to 0, and so this is same, this is also the same, b0, b1, b0, this is the same. Okay, so we can use this algorithm based on these informations. Okay, and so we need to create the figures, and so for I is equals to the 1 to length of frequencies, which means that we plot the whole frequencies in here, and after that the f should be assigned to the what, the frequencies, to what, the I, and x can be assigned to a times sinus signal to pi, f and t and phi. Okay. And after that y zeros n 1, and also we need to apply this signal to what, to n, and okay, y j must be equals to the what, the b0 times x j plus b1 x j minus 1 minus a1 times y j minus 1. This is the first order filtering. Okay, and after that we need to build the subplot values in here, just like this one, the length of the frequencies values, and 1 and I, right? This is subplot, and so the plot should be given in here, n times t and x and b, this is the marker of these terms, and n times t and y and the marker of the red. Okay, and title of the what, the percentage d hertz input, and filtered out signal can be given in here with the f value. Okay, but we need to give the s printf in here because we need to fill the percentage d as printf. Okay, so x label time, y label amplitude, and also the legend of these terms, the input signal, and after that filtered signal, and the location best. Okay, so the grid on should also be given in here. Okay, and so if I rerun this code for under the different frequency responses, and then we will have to what? See that in this signal our sinus is tracked with the what? With the same one, because this is the 5 Hz signals, but at the 50 Hz signal there are some losses in here, just like this one, up to what? Up to 0.7. okay, but at the 100 Hz signals, just see that we have the what? 0.4 amplitude for a given 1 amplitude values. Okay, and the cutoff frequency is the 550 values, right? And so what's the difference of this algorithm based on these informations, these important parameters? Because if I choose the 200 in here, and so there's a lot of energy losses in here, just like this one. See, 0.14 or 0.2 for a given 1 amplitude values of this signal, and so we will apply some filters based on this information, and then we can build the digital signal processing. And so what is the code you should be implemented on the embedded system? Just use the following difference equation, and then the filter is done. Okay, this is simple. That's all, guys. This is the end of this low pass filter design in the discrete domain. And so I hope you have learned everything about what I'm saying in this lesson. Have a good day.